All right, here we go with the last part of the video for 3.5. So we've been talking about derivatives of trigonometric functions. So we're just going to do some higher order derivatives on this. So first of all, a little technique for remembering these things, because you want to remember these derivatives here. Um, First of all, these are the 6 rules we looked at. And this is the way I look at it. It's the function begins with the letter c, then the derivative is negative. So that just means these are all cofunctions. Cosecant, secant, cotangent, they're all what we call cofunctions. And this one has, hold on, not the secant, okay? Not that. This one. They got to begin with a co, okay? There we go. So what I'm trying to point out on this is they all have negative answers, okay? So I just say if the function begins with the letter c, then the derivative is negative, okay? All right, and then these are the basic things you learn in trig. So the cofunction of the sine is the cosine. The cofunction of the tangent is the cotangent. That's built into the naming system. And the cofunction of blank, I think that was meant to be, what am I left over with? The secant is the cosecant. Okay, so down in this chart I put together, this sort of shows you the pattern on this. So if you remember, the derivative of the sine is the cosine. Okay, then the derivative of the cosine is the negative sine. Okay, so it's a negative answer then. And what I want you to notice on this is these are cofunctions. The answer to the derivatives are cofunctions, all right? And the tangent works the same way, so the derivative of the tangent is the secant squared. Well, when you do the derivative of the cotangent, it's a negative, but it's also the cofunction of the secant. So you have secant, cosecant. Okay, nice little pattern. Derivative of secant is secant tangent. Okay, well, the cofunction of the secant is the cosecant. So look at this. The cofunction of the secant is the cosecant. The cofunction of the tangent is the cotangent. So see, these things have a nice pattern. Math is always just sort of full of fascinating patterns, and that's the way that works out. So that's one way to remember that. Generally what I do, and what you'll find as a student, is, you'll remember this and this because you use that so often. But if you can just remember this tangent and then the derivative of the secant, then you can figure those out. Okay, they just follow the pattern. Secant squared, cosecant squared. Secant tangent, cosecant, cotangent. Okay, that's what I wanted to show you. Okay, now going to high order derivatives, we've talked about just a little bit already in this class. So just the nomenclature of this is f prime of x, f double prime of x, f triple prime of x, and then we just say fn of x. So if you had a fifth derivative, then you usually just represent that like that. In the Leibniz notation, dy over dx for first derivative, d2y over dx2, and so forth, okay? And this is just the way that you represent higher order derivatives, okay? So we're going to look at a few of these things. So this one right here, this example, you're looking at the third derivative. So you're just going to start off like this, okay? We have dy over dx, like this. And the way we do this is, we're going to learn something in the next section called the chain rule. So I'm getting a little bit ahead of me on the chain rule, but I'm going to go ahead and explain it. Our textbook doesn't really do the chain rule until after this section. I wish they would have done it a little earlier. So when you do this, if we just were to do the derivative of the sine, the derivative of the sine is the cosine. So what you would end up getting is the cosine of 2t. Now what you're going to learn is something we call the chain rule. And what that means is, since that itself is a function, you also have to multiply by the derivative of that function. All right, so the derivative of 2t is 2. So what you get then is the first derivative would be 2 cosine of 2t. All right. So if there's a function inside of a function, you always multiply by its derivative by the chain rule, right? And then the second derivative, which we represent this way, would go like this, okay? We just start the derivative again. Well, that's a constant, so remember, if it's a constant multiplied by a function, you just write it down. Then we do the derivative of this, okay? The derivative rule for the cosine is negative sine of whatever, all right? But since that 2t is a function itself, you multiply by its derivative, so the derivative of 2t is 2. Again, that's called the chain rule. So if we work that out, you'd have 2 times 2 and then the negative, so that would be negative 4 sine of 2t like that. All right, so what we got so far is we got our first derivative, our second derivative, then we're going to go on to the third derivative. You'll see this kind of thing, like in this class, you know, we've already seen the velocity as a first derivative, the acceleration as a second derivative. When you take Calc 2, you'll start getting into what we call Taylor polynomials, and then you start doing higher order derivatives. You can get into higher order derivatives with that too. Okay, so now we're going to do a third derivative. So it's the same idea. This is a constant, write it down. The derivative of the sine is the cosine, so that becomes cosine of 2t, but again, the chain rule says since that is a function inside, you multiply by the derivative of 2t, which is 2. So you would get negative 8 cosine of 2t would be your third derivative then. Okay? So here's our derivatives. That's your first derivative, that's your second, that's your third. And what you're going to notice on these things, and you'll start seeing this like in Calc 2 when you'll start seeing patterns a lot of times on these derivatives. So it's just going to rotate between cosine, sine, and cosine. And then the numbers 2, 4, 8, looks like those things are getting doubled. So there's a nice pattern to that. And a lot of times you'll find patterns, of course, all through mathematics. Okay, the next one is a second derivative. And I'll kind of show you how the chain rule works on this. And what we have to do on this is you probably want to write this as cosine of 1/2 x to the second power, like this then, all right? So what we're going to do here is we're going to start by doing the first derivative, okay, like this. And this is can be thought of as a power rule. I think our textbook already explained an extended power rule, and sometimes textbooks do that. I wish they would just show you the chain rule and be done with it and not worry about that rule. But this is just like the power rule. So in that first derivative, you bring the 2 down, and then you leave what's inside alone. You don't do anything to that. And then, like you're used to doing, of course, you subtract 1 from the exponent like that. But there's more, okay? The chain rule says that since there's a function inside, you also have to multiply by the derivative of what's inside. So we have to do the derivative of the cosine of 1/2 x, and then do that then, all right? So we'll bring this down. This just comes down. That will be 2 cosine 1/2 x. Now this derivative here, when we do this, the derivative of a cosine is a negative sine. So that will be negative sine 1/2 x. Okay. Then you got to multiply by the derivative of this, and the derivative of 1/2 x is 1/2. Okay, so it's kind of what we call a chain rule and a chain rule. All right, so what we have here is the 2's will cross out, so it looks like we're left with negative sine 1/2 x times cosine of 1/2 x like that. All right. So that's how you would do the first derivative. Now you'd have to go on to the second derivative, okay? All right? And I think in the next section you'll get a lot more practice with the chain rule. The way the book is, I have to sort of introduce it here a little bit. But that's fine. So now we go on to the second derivative. So when I move to the second derivative, this will go like this then. But this is a product rule. So we got to use the product rule where we do first derivative of second plus second times derivative of first. Okay, so we're going to do that. Now I'm just going to kind of put the negative out at the side here. That's just the way I'm going to choose to do that. All right, and you can think of that as a constant, so just write it down. So we're going to put the product rule. We do the first multiplied by the derivative of the second. And when you do the derivative of the cosine 1/2 x, you got to do the chain rule. Left off my x there. Okay, now we go plus the second. And then we multiply by the derivative of the first. Okay, then we'll go ahead and get that all put together. Okay, so that is your chain rule again, where we just did first function, derivative of second, second function, derivative of first. Okay, now what I'll have here is this will go like this. So we're just going to bring this down. I'll bring down the bracket, so I have sine 1/2 x. Okay, the derivative of the cosine, so when we do this, that's a chain rule. So the rule is derivative of cosine is negative sine. So we have that. Then you got to multiply by the derivative of what's inside, which is 1/2. So that takes care of that. Okay, then we bring down the rest. We have the second. That comes down. And then when we do the derivative of the second, the derivative of the sine is the cosine. And then you got to multiply by the derivative of 1/2 x, so that's 1/2. Okay, so what I did is that kind of gave me the derivative of the second. This part right here gave me the derivative of the first. Okay, so I've got that put together. That's the derivative. Then we'll just clean this up a little bit. So it looks like what we're going to have is, and I'm going to go ahead and just distribute the maybe the negative through there right now, or we can wait till later. Let's just bring this down. So this would be 1/2, negative 1/2 actually. You have a sine times sine, so that's a sine squared 1/2 x. Okay, then we have plus, then we have a 1/2. And then we have a cosine times a cosine, so that's cosine squared 1/2 x like that. All right. There's a few identities that could be used here. I'm going to go ahead and just show you on this too. So, and once you get working with these trig functions, you'll kind of remind yourself of these identities. So I'm going to write this like this. I'm going to write this as negative. I'm going to put this backwards. I'm going to take out a 1/2 actually. And we'll go ahead and do that. So we have negative 1/2, which I'll take out. I'm going to leave that negative. Then I'm going to do this backwards. So I'm going to do, let's see, like this. I'm going to write this as cosine squared 1/2 x, and then minus sine squared of 1/2 x. Now, anytime that you do a factoring, just kind of make sure that you're doing this right. So notice we have I think I may be off on that just a little bit there. That was a negative already there. Okay, that was already there in the problem. Okay, so yeah, so I'm okay. All right, so I just kind of making sure this negative's already there. All right, so all I did was just took a 1/2 out, so I still have the 1/2 sine, and then I've got the cosine. Okay, like that. All right, so I haven't done anything. I just took out the 1/2 and left everything the way it is. Okay, so we have an identity that says this. The identity that you learned in trig is the cosine of 2x is equal to the cosine squared of x minus the sine squared of x. Okay, so you could actually use this identity here. All right, that identity would be cosine, that would be actually the cosine of 2 times 1/2 x. So with this identity, you'd end up with negative 1/2, and then you could change this to cosine of 2 times 1/2 x. So I'm applying that identity right there. So that would give negative 1/2 cosine of x would actually be the answer of that higher order derivative. Okay, so you get into some trig identities when you're dealing with these things then. Okay, so that'll you use the trig identity, and one thing I wanted to mention on that is, you know, the argument of this, you're doing double that. So the argument of this was 1/2 x, so that's why I did that. Okay, and then 2 times 1/2 x, of course, becomes x. Okay, so let's see. Let's go through, and what I'm going to do on this next page is just kind of run through a little bit more with this. You're going to see a pattern that exists on higher order derivatives, so we're just going to do this. If you have y equals sine x, first derivative is negative cosine of x. The second derivative, you'd still have that negative. The derivative of a cosine of x is a negative sine x. So on your second derivative, then you would be back just to the sine x again. All right. Okay, now we do the third derivative. So the third derivative of sine, what in the world did I do? That is not right. Brad, pay attention. The derivative of the sine is the cosine of x. All right. Now the derivative of the cosine is the negative sine x. So it goes like that. All right. So now we just keep going. Now we're going to do the derivative of negative sine x. So we just write down the negative. The derivative of sine x is cosine x. So far we've got that. We're going to see if we have a pattern on this then. So now we move to the fourth derivative. We have a negative. Just write it down. The derivative of the cosine is a negative sine x. So this takes you back to sine x. All right, then you're going to start seeing a repetition. The derivative of sine is cosine, and then the derivative of cosine is negative sine x. So you'll see a pattern on this then. You're going to notice it looks like the first derivative, second, third derivative, and then when you get to the fourth derivative, you're back to where you started, and then it's just going to start repeating itself. Okay, so those things rotate. So what I'm going to have you do is just try these derivatives here. I'm going to have you pause the video, and I want you to do the higher order derivatives on these. You got to apply the chain rule a little bit with this one as we go. So you're kind of just now learning the chain rule. So I'll see how that goes, and then the chain rule, like I said, will be a big deal in the next section. Okay, so pause and see how you do. Okay, so let's see how we did. The very first one, we're using the chain rule. So again, the first derivative, you just write down the 2. Derivative of cosine is negative sine of 3t. You leave that alone. But then you multiply by the derivative of 3t. So you get negative 6 sine 3t. That's your first derivative. You move to the second derivative. You write the negative 6 down. Derivative of sine is cosine of 3t times derivative of 3t is 3. So that's negative 18 cosine of 3t. All right, third derivative, write the negative 18 down. That's a constant. The derivative of a cosine is a negative sine. And then do the derivative of 3t to get 3. So 3 times negative 18 is negative 54 cosine 3t. Okay, hold on. God, I'm doing stupid things this morning. All right, so that would be sine. I caught my mistake because I knew they were going to rotate. So I just noticed that. So I wrote it down incorrectly. So these things triple, so you'll see 6 times 3, 18 times 3. That's kind of a nice pattern that exists on that problem. Okay, so those should be your first 3 derivatives. The second one, number 2, let's see, or part B, the derivative of a tangent is a secant squared. That's a rule we learned, so that's your first derivative. Then you want to probably write it this way so you can do the chain rule, or if you prefer, the extended power rule in this case. So second derivative, bring down the 2, subtract 1 from the exponent, and then that's part of it. And then you always got to do on that chain rule is you got to do the derivative of what's inside Z. Okay, so we bring down the 2 secant of x, and then the derivative of secant is secant tangent. So we learned that. So you end up with 2 secant squared x times tangent x, and that's a fine answer. You could I don't think there's any need to do this, but we have the identity that the secant squared is tangent squared plus 1. So you could do a substitution, but there's really no need to do that. Okay, so that's what we hopefully got on the first two there. All right, and then this one you got to use an identity on. I mean, you could bypass that, but it would be harder to get that second derivative. So, like when you start working with these trig functions, you might want to have a sheet with your identities on it because you want to start reviewing those identities. So you would do a product rule on this problem for your first derivative. So you have two functions, you have the first and you have the second. Okay, so I'm just going to build this in the product rule then. So I go take the first times derivative of second plus second times derivative of first. So I'd have sine t, derivative of cosine is negative sine t, plus cosine, derivative of sine is cosine t. So you would end up with negative sine squared t plus cosine squared t. If you write that backwards, well, then you have to realize that, well, we have an identity for that. So the cosine of 2t is cosine squared t minus sine squared t. So that's really the best way to write that first derivative because it's simpler. And it's easier to do the derivative, the second derivative. So when we do the second derivative here, we would have the derivative of cosine is negative sine 2t times the derivative of 2t is 2. So you should get negative sine of 2t as your second derivative. Okay, got to use those identities. And the next one, I just wanted to show you the pattern. So I gave you the function y equals cosine x. First derivative is negative sine x. Second derivative is negative cosine x. All right, because the derivative of sine is cosine. And then you write the negative down. The derivative of cosine is negative sine. So you'd have negative sine, so you're back to sine x. And then when you go to the next derivative, derivative of sine is cosine. So it's going to rotate. Nice pattern. Sine, cosine, and then the signs alternate too, see? Okay. All right, so that'll take care of that. I'm going to move to the last page here, just do a couple of applications. Pause here if you need to look at these and think over these. Otherwise, I'm going to move to the last page. All right. So just a couple of applications. You'll see this a little bit in your homework. So we have the function y equals cosine squared of x. We're going to find where it has a horizontal tangent line, and we're only looking at that interval right there. So what happens on this, something is causing this thing to mess up all the time. Okay, all right, so I think I've got everything situated here. So, all right, so the thing that we learned here, maybe, there we go. Okay, accidentally pressed a button on this and it messed everything up, I think. All right, so what I'll show you on this then is we have this function, and we want to figure out where it has a horizontal tangent line. So the key thing is, when you have a horizontal tangent line, the slope of that tangent line is what? It's 0. Okay, that's the key on that then. All right, so what we're going to do is we're going to kind of do what we've been used to doing on this is go ahead and start with your derivative and set that derivative equal to 0. So to begin with on this problem, we have y equals cosine to the second of x. I would rewrite that, though, as cosine of x all to the second power. And that way I can use the chain rule to do that derivative then. Okay, so what I go ahead and do on this then is the first derivative, dy over dx. Okay, we're going to do this kind of like the power rule, so bring down the 2. Leave the cosine alone. That goes to the first power. All right, then you got to do the derivative of what's inside. So we have to do the derivative of the cosine of x. All right, so what we'll have is we'll have 2 cosine of x. That comes down. Then the derivative of cosine is negative sine of x like that. All right, so if I write that first derivative then, I'm going to have negative 2 sine x times cosine x like that. All right, so we got the first derivative. Now what we're going to do is you got to dig to your trig background. We got to solve a trig equation. So what we're going to do is, since the slope of the tangent line is 0, And since the slope of a tangent line is represented by the derivative, then we set that derivative function equal to 0 when we solve that equation on this interval. So you'll have to kind of look at your unit circle and everything. Okay, so this goes like this. It's already in a factored form. You don't have to do this. You can just ignore the -2, or you could divide by it. Okay, so you just end up having sine of x times cosine of x is equal to 0. Okay, so you do that. And then the third thing you do is just kind of look at the unit circle. So we set each factor equal to 0. And then we'll look at a unit circle. I'll go ahead and just pull up a unit circle here real quick. Okay, so presto, there's my unit circle. You can refer to one as you go. The thing in this class is you want to be able to create a unit circle as you go. You don't want to have to refer to it all the time. But for teaching this, it's just as easy to just display one. So the idea with this is you got to remember, just a quick review here, the sine is the y value on a unit circle. So what you're really looking for is, where is y equal to 0? Well, y is equal to 0 in two places. So on the interval 0 to 2 pi, we include and exclude. Okay, that's got a bracket, so we're including that. And then we're excluding this. So it looks like there's two places this happens. So it looks like at 0 radians and also at pi radians. So those are the two places where the sine is equal to 0. Okay? So we're going to have a horizontal tangent line at 0 and pi. Okay, then we do the cosine, and you want to recall that the cosine is the x value in a unit circle. All right, so if we look at where x is 0, that occurs in these two places. So that would be pi over 2 and 3 pi over 2. So in this case, we would get the value of that angle is either going to be pi over 2 radians, or it's going to be 3 pi over 2 radians. So this would be all the places where the horizontal line's tangent is horizontal, or the tangent line's horizontal. Okay, so the answer to the problem would then be, you just kind of write this out in a set if you want to, would be like 0, pi over 2, pi, and 3 pi over 2 radians. Okay, so that would be all of the places where the tangent line's horizontal. So a good way to close off a problem like this is to just verify it on a graphing calculator and kind of see what we got here. All right, so what I'm going to do with this is we're going to put this in the calculator. All right, so I'm going to take everything off of here, and we put this in like this, so we need to put in parentheses cosine x, and then square that like that. So that's how you would want to put that in the calculator like that then. Okay. All right. Then for a window, you want to make sure you're in radians. So make sure that you're in radian mode. Press your mode button. Then for the window, we're going to go like this. We're going to go 0 to 2 pi. The problem did give you the interval 0 to 2 pi, see? So we do that. Scale it by whatever you want to. I'm going to scale it by pi over 2, like that. And then for the y's, let's just do something like -2 to 2. And scale that by 1, and that's probably a good enough viewing window for this problem. Okay? All right, so I got that, and then just type graph, and then that's what the graph looks like then. So I'm going to slide this graph over here and just show you a couple of things that I find on this then. Okay, so what you'll have on this, we can trace out every one of those solutions. So if we just traced at 0, well, you can tell there's a horizontal tangent line there. All right, if you drew the tangent line's horizontal. If you go to pi over 2, so if you trace it pi over 2, same thing, you have a horizontal tangent line. Trace it pi, same thing. 3 pi over 2, same thing. So you might want to just kind of sketch a little graph on your notes. I mean, you don't have to, but it's worth doing. That you end up having this kind of situation here. So this is 0, that's pi over 2, that's pi, that's 3 pi over 2. So what happens on this is visually you can tell that your tangent lines are horizontal at those values then. All right, so visually you can tell you're correct. All right, very good. So let's just do this last thing here. And on this last example, we're going to do an equation of a tangent line, which we've done already plenty of times. So typically what you do in this is if you're asked to find an equation of a tangent line, the point slope formula ultimately will get you there. And you have to know these things. So you have to know the slope. And what that is that really is going to just be the derivative. In this case, that's y prime. And that will be y prime evaluated at pi over 4. I have to give you the x value. So that's what's going to go there. You also have to, of course, know this. And you have to know this. All right, so it looks like what I've given you so far is I've given you x is pi over 4. So I got to figure out what y is. So that's kind of how I'm going to start the problem. All right, then I'll go back to that formula in a minute. So now I'm going to go ahead and do this. I'm going to go ahead and just evaluate this function at pi over 4. So I need to do the tangent of pi over 4. Okay, now recall that the tangent is y over x. So if you look at this unit circle, you would be here. Y would be this, x would be that. So y over x would be 1. So you're just taking root 2 over 2, that's easy to do in your head, divided by itself. So that gives 1. So what that means then is a 1 is going to plug in there then. All right, so what we really found here is what we would call the point of tangency. The point of tangency would be pi over 4, which I gave you, and then the tangent of pi over 4 is 1. All right, so now we go to step 3, and step 3 we need to do the derivative. Okay, so when we do y prime, the derivative of a tangent, derivative of tangent is secant squared of x. All right, then what we got to do is we got to evaluate that. So if we do the slope of the tangent line at pi over 4, that's going to be equal to, and you just do this like this, you do the secant of pi over 4, and then square the whole thing. Okay, like that. All right, so we got to work that out. We can work that out with the unit circle. So the secant is 1 over the cosine. It's the reciprocal of the cosine. So the cosine of pi over 4 is nothing more than the x value. So that's square root of 2 over 2. Therefore, the secant, since it's the reciprocal of the cosine, that means this would just be 2 over root 2 squared. So that's what the secant is. Okay, then what you could do here is this basically. All right, so if we square this, we would have 2 to the second is 2. Come on, Brad. 2 to the second is 4. Okay. And then square root of 2 squared is 2. So that's equal to 2. So that slope of the tangent line then is going to be 2. So you got to do the derivative, and you've got to evaluate that derivative at pi over 4. So what that means is, to complete our problem then, is slope of the tangent line is 2. So now we have everything we need to know. Then we can go back here and finish this up. So we'd have y minus 1 equals 2 times x minus pi over 4. Okay, and we're just going to solve that for y. Then we'll take a look at this in the graphing calculator and see if this makes sense to us then. So this will be y minus 1. I'll do a distributive property, so 2 times x is 2x. This will be 2 pi over 4. And 2 pi over 4, of course, reduces to a half. So I'll have y minus 1 equals 2x minus pi over 2. I can add 1 to both sides, so I get y equals 2x minus pi over 2 plus 1. And, it's good enough to just leave the answer that way. That's fine. That's a good-looking tangent line to me. Or you could, put that together with a common denominator. I don't think there's really any need to do that, though. So let's close this off just by doing a graph to verify this. So what you'd want to do is graph the tangent. So we'll do graph of tangent of x. We can use probably the same viewing window for the last problem. It might be wise to Maybe make the y's a little bit bigger. I'm just going to maybe go -5 to 5. Just kind of see what that looks like. Then establish your graph like that. And then what we'll do is we'll go to y equals and we'll go to y2 and then we'll put our answer in. So our tangent line is 2x minus pi over 2 and then plus 1. Okay, so get that graphed and see what it looks like. Okay, looks like a tangent line. All right, and what you'd have here, if you trace at pi over 4 is the place where we were interested in the tangent line. So if I trace at pi over 4, okay, it's going to blink right where it's supposed to. Okay, so you can tell visually that that looks correct to you. All right, so that's it. All right, you can draw a graph on this if you want to, but mainly what I want to do on that is just kind of show you that this is correct visually. Okay, so that'll wrap that up on this. The only thing that's that I had to go over on this a little bit is the chain rule. I think in your homework you probably don't see chain rule popping up on this, but I had some examples like this that I thought were good examples, so I thought it'd be worth just going ahead and introducing you to that a little bit. But that's what you get into in the next section. Okay? All right, good luck.